Come on, let's hear it. Let's talk about planes, shall we? What could possibly go wrong? I want to talk about some of the things we've learned about plane security over the last 6-7 years. Bit about me before we go there. I am a private pilot. I'm also not a very good private pilot. I've had a few issues over the years, so I've successfully landed at the wrong airport. I've had an engine fail on me. That was fun. The undercarriage didn't come down a couple of times. I very nearly crashed into other planes 3 times. And I've also told air traffic control once I was there, when actually I was there. That caused chaos as well, so that was problematic. Fortunately for all of you, I originally intended to become a commercial pilot. My career took a bit of a change in 2002, and instead of going and flying you around, I ended up staying working in light aircraft, general aviation, started a pen test firm. I do still fly. Some of my favorite planes, top left you've got the Piper Cherokee 6, which you can load with 6 people and stuff and fly it anywhere. I even flew it to Courchevel-Alteport in France, which is the 7th most dangerous runway in the world. If you get it wrong, you roll off the top, crash into the snowbank, and the people in the pub, which isn't shown just about there, all give you a massive round of applause. Anyway, I also went out to the Baltic states to learn to fly old Russian airliners. That's the Antonov AN2. You can get a car inside that. Brilliant fun. And twins as well. Who are we? Well, you know us as a team of about 130-something of us. A bit unusual. There's a good few pilots on the team. Along the way, we've guided Boeing and advised them. We also co-founded the Aerospace Village at DEF CON, where I've just come back from, so a bit jet-lagged, and done lots of weird research. But anyway, before we go there, a big caveat is there's something about aeroplanes and journalists. As soon as you say plane hacking, the world loses their shit. So we have to be really, really careful about disclosure. Now, believe it or not, it can take up to 2 years to test, evaluate, and prove that a software update isn't going to cause a blue screen of death in the air. It's one thing fixing a security bug, but knowing that system, that update, isn't going to brick the plane when it's in the skies is probably more important than the security flaw. That took us a while. Now, some other tropes that we keep seeing around being able to hack a plane from the seat-backing economy, it just doesn't work like that. Even if you could, which you can't, and I'll explain why, there's still pilots up front, so when the systems start going haywire, which they won't, they can still land the plane safely. But some of the reports that you see in the media over the last few years have been really unhelpful, some of which have got grains of truth but got blown out of all proportion, others which are just frankly made up, or just don't take account of some of the logical designs and the architectural designs of aeroplane networks. So, moving on a bit. Number one, why can you not hack an airplane from your seat? Well, there's lots and lots of different connectivity systems in a plane. I'll walk through these. But probably the most important thing to know is that, unsurprisingly, there is really good domain segregation on board the plane. There are broadly four domains. In the back, the bit where we are, you start off with the Passenger Information Entertainment Services domain. So that's your in-flight entertainment system, cabin Wi-Fi. Also, the newest one, probably the POD, Passenger-Owned Devices domain. That is your phone and your laptop. Those are completely segregated from the next domain up, which is the Airborne Information Services domain, which is for the cabin crew. And so if you walk onto a plane, maybe an A320, if you look left at the wall as you walk on, you'll see the Flight Attendants Panel, or FAP, and that sits on the AISD. It can do some more things. So, for example, you can do certain types of messaging to the ground. Maybe a passenger's having problems, for example, and you can control various cabin systems. And then up front, you have the aircraft control domain. So that's the one that does the uppy, downy, lefty, righty stuff. And it is completely segregated from all the other systems on the network. The one bit of data that does cross those networks is the moving map display. So it takes a feed from the flight management system, goes through a one-way data diode in the case of the A350, which is one way for a bloody good reason, so you can see on your moving map where you are. On older planes, there is slightly more information that crosses the domains, but they tend to be discretes. And by that, I mean literally sensors going, that thing's on, that thing's off, just as a redundant backup. You cannot go from the cabin into the control systems. So the sort of connectivity you're going to find, so you're going to see SATCOMs, and SATCOM was in place long before you and I had access from the cabin for the crew. You'll find the in-flight entertainment system, which has some connectivity. There's various other reporting systems, so ACARS, I won't touch on too much. ADS-B you'll know about from Flight Radar 24. We're going to not talk about TCAS, because that is Sean Guthrie's talk at 5 o'clock. Go and see it, it's really good. And then we'll talk about CPDLC and various of the other devices. One that's unique to Airbus is FOMAX. That's the Maintenance Access Exchanger, built into all modern Airbus planes by default. And that is a really quick way of getting real-time maintenance data out of, for example, the engines, so that you can do predictive maintenance. So if you see something starting to degrade over time, you can get the parts to the next airport really quickly, so we never have a problem, we never get delays. So it only goes one way. The other big reason you can't hack planes from the back is the protocols and architectural designs of various planes. So on older planes, so the Airbus A320, 737, 747, you're going to find a protocol called ARINC 429, which has been around for a lot of time. It's pretty simple. If you go to the avionics or EE bay, you'll find lots of LRUs, line replaceable unit. And every one of these boxes is demountable quickly, so if it goes wrong, we don't go and fix it, we just put a new one in and then fix the broken one on the bench later. Line replaceable unit. So one of those might do the radar, another one might do the left engine control. So it's not really a network as such, it's a bus. The source can talk to up to 20 sinks, so again, lots of wiring as a result. That wiring is quite heavy, which causes problems. It's quite simple to do. You will find interfacing ports like these. These are what are called amphenol connectors. You'll notice they've actually got locks on them. There's a bloody good reason for that, is RJ45 clips don't do so well in turbulence. They tend to fall out. So we use either these amphenol connectors, which screw in, lock in, or we use quadrax connectors, which also lock in place, so they don't fall out mid-flight, which would be kind of bad. You'll find these in the avionics bay. This one's in the overhead in the cockpit of A320. You can interface these with something as simple as a couple of probes and a picoscope. So you can read them quite easily if you know what you're doing. Problem with ARINC 429, it was heavy. So we had a lot of wires, which means we can't take as much cargo and as many people. So for the 777, we started to see a new protocol develop called ARINC 629, which was an inductively coupled bus network. These are the couplers. I've got a few. So rather than having lots and lots of cables going everywhere, you could couple onto an inductive bus. So you connected your LRUs onto bus A and bus B, saved enormous amounts of cabling weight. But it's only used on the 777, as a result of which it's really hard to interface with. It's really expensive to interface with. There aren't really open source tools, and the decoder that we use costs nearly $30,000 just to talk to the network. So it's a huge obstacle. But things then changed. We then moved with the development of the Airbus A380 to AFDX. So that stands for Avionics Full Duplex Switched Ethernet. And you're going, ooh, Ethernet. We know about Ethernet, don't we? That sounds like a protocol we know about. However, our DEF CON talk, which we've just done, was all about how hard it is to interface with AFDX. It's Ethernet, it's not IP. So a hub will work, but a switch won't, because we don't have any concept of an ARP table. So it's actually really difficult and challenging to interface with AFDX, but certainly the level of technical challenge is a lot less than $30,000 of decoder. So we've published that talk. It's there. I won't go through the detail. You can find it on the DEF CON media server. It tells you all about how you interface with these latest flight control protocols. Oh yeah, you're also going to find CAN as well. So those of you who know your way around cars, you know about CAN, the Controller Area Network. You also find CAN, but only in the overhead panel in the A380. So if you want to interface with the overhead, great, take CAN Spy, go and have a play, or not. Anyway, above all of this, please be really, really careful. We got access to lots of airplanes during COVID. A lot of the breakage yards were laid up. A lot of the planes couldn't be parted out, so we had perfectly functional aeroplanes that were never going to fly again. So it's a good candidate for playing around with. We had to pay, so we had to pay the breakers yards for power, to fire up the auxiliary power units, to power up the systems, but then it meant we could play. But you've got to be careful, because planes run 400 volts. That's quite a spicy voltage, so I wouldn't recommend putting your fingers in any way you shouldn't. You can increasingly get hold of old line replaceable units, occasionally on eBay, more likely from a plane breaker. Problem being is if you want something that's still usable on a live aircraft, it's got enormous value as a certified product. So you're going to be talking $2,000 to $10,000 per LRU. So you're much better finding something old or going and playing on a retired plane if you can. Most of the time, my job was to stick pins in things and see what happened. Yeah. Let's talk about some of the myths and other tropes we see around aviation. So I want to start with a couple of fun things. Now, I had to rewrite this talk because it seemed everything happened in the last 7 days in aviation cyber. So I had a talk, it's completely different now. Anyone saw the Delta 591 incident? Great. So looks like some spanner bought a Wi-Fi pineapple at DEF CON and span it up on the flight home. That's it. The reason we know about it is there's a really good website. So ACARS, as a messaging protocol, is open. It's broadcast. You can all see it. And ACARS Drama is a really cool website that pings up the ones that are interesting. Often things like passengers had an issue. Sometimes you see credit card data in ACARS messages, all sorts of weird stuff. But this one was unusual. We've got a bunch of cyber types who jammed our in-flight Wi-Fi and broadcast their signal. Yeah, so what? Nothing actually happened. None of the cabin systems are actually vulnerable. Someone de-authed some people and tried to broadcast. But the world lost its mind. And I'm like, no, it's okay, the world, don't worry about it. It's just someone de-authing. You cannot hack a plane over Wi-Fi. What could you hack from the cabin? Honest answer is not very much. So the IFE, there have been a few cases over the years where people have found vulnerabilities. Actually, amusingly, Andy Gill found a vulnerability in one of the IFEs a little while back. It was Android-based. We've had some compromises too, but what's the worst case? So you could take it out, so it pisses everyone off. One story I'll talk about in a little bit is about broadcasting rogue content. That could make things a bit spicy, but what's the worst case? Bit of bad PR. There's one other thing you could do is the pilot's flight bags. You could continually try Bluetooth pairing requests, which are a bit irritating, and if you got it at the right time, you might distract the pilot, but not really. There's not much you can do. One potential thing you could do, now this came from a thought process, is could you use an IFE hack to put a plane out of trim? So what, for example, if you could get broadcast a message that said to all the IFE screens, there's a bomb at the front, go to the back. Well, frankly, if there's a bomb at the front, you're fucked, right? Right? So the cockpit falls off. Brilliant! Okay, anyway, go to the rear. So what would happen? And we actually did a thought exercise looking at the load of passengers and see how much weight you could move from the forward to the back. And because the plane's moving at quite some speed, you've got a lot of air going over the elevators. So even if, on a smaller plane, everyone moved from the front to the back, you've still got enough elevator authority to stop it, except in the interesting case of the A380, but only on finals. And that means final approach after a long flight. And the reason you have to do it on finals is there's actually a fuel tank in the tail fin of the 380. So if you start getting trim out of balance, you just pump fuel forwards, and all of a sudden the plane's absolutely fine again. Unless you're at the end of the flight and haven't got much fuel left, in which case you could, in theory, do that. Now, is that actually going to happen? No, it's not. But that's about as bad as it could possibly get. So what about other ways to make planes do things that you probably don't want them to do? And I've got a few examples here. We've got not the Netflix way, which I'll talk about in a minute, the ARINC 429 way. We've got a way using CPDLC and also potentially using electronic flight bags. And I'll walk you through these. First one, I don't shout at my TV. I'm not an angry person, but there was a documentary on Netflix about the MH370 disaster, which suggested that instead of being the widely accepted version of pilot murder-suicide, actually it was a Russian Black Ops team that were taking a plane down in order to distract from the invasion of Crimea at the time. And what they postulated, I've since spoken to the guy who wrote the documentary, we did a podcast together, kind of explained why many of his theories didn't work, is the 777 is quite unusual, is like the 747, you can actually access the avionics bay in flight. You can do it from the cabin. Everywhere else you have to go outside the plane, or in the case of the 350, the access bay is inside the cockpit, so it's safe. So the idea was that they created distraction, all the crew go that way, special ops guy goes into the avionics bay down the hatch and then puts everything back and no one notices. Yeah, right, okay, fine. And they suggested, and this is a screenshot from the documentary, that the Russian attackers connected a Windows laptop to the avionics using an Ethernet cable, okay, and remember we don't use Ethernet cables, they actually look much more like that. So again, Ethernet would not work. And then I zoomed in, I got a still freeze frame, and they used a UEFI BIOS exploit in the text and some DNS exfiltration, because it's always DNS, right? Every time. Okay, so forget made up stuff. in the TV and movies. What about some real ways? Okay, there's a really interesting paper, and this is why I had to rewrite my talk, that came out on Thursday, right? This is hot off the press. It's a really interesting piece of work, and I thoroughly recommend you go and read it. It involves some researchers who spent nearly 6 years gathering bits and bobs of aviation hardware, some expensive stuff, put it together, and did a really interesting project trying to figure out if you could do something using ARINC 429. Now, we've always said once you had physical access to the avionics bay, then frankly, all bets are off, as long as you've got enough time. So what they did is put together a test bench to recreate this in order to inject messages, particularly around to the flight management system, to simulate information coming to the cockpit display unit. Now, the CDU is the thing you'll see on the pedestal. That is it. It's not an MCDU. It's actually just a CDU. That's how you program the flight management system. It's how you program things like weights. It's how you program things like your flight plan. And they've figured out a way, if you had a few seconds of access to the avionics bay, so again, you've got to be on the apron, you've got to have security, you've got to have social engineered your way on. You could get a connector into a particular port called the open maintenance connector, which is inside the avionics bay, and you could, in theory, start putting data onto the network. And on the back of that, you could start tampering with the information that the pilots were seeing or tampering with the flight plan. So, for example, this is an example they've got. They've actually showed changing active nav databases, changing weights and fuels. So you could, in theory, inject a new flight plan. And if the autopilot's on, then the plane will then follow that flight plan. Now, people are going to notice, mostly because air traffic control said, go this way, and you're going that way. Okay, that's a problem. And the pilots eventually will notice. And there was genuinely a case a few years ago where some pilots were sent the wrong flight plan and just accepted it. Why challenge the flight plan? And they only queried it, they were coming out of the UK, and they queried it when they were the wrong side of Ireland, when they should have been over Europe. But hey, they turned around, went back, got some more fuel, and went back where they should have done. So you do tend to notice this. But there's also some consequences around some of the information they could inject around messing around with the zero fuel weight, outside air temperature, and loading. So for example, you see the zero fuel weights up there. That's on the 737. It's showing about 60 tons. So that's how heavy the plane is without fuel and passengers in. So if you can tamper with that, there's some interesting consequences I'm going to come back to. That's quite important. Other ways, let's talk about the CPDLC way of doing crazy things. And this is hot off the press. This also happened just last week. It's really interesting. That's the paper. It's presented at the Usenix conference. I think on Friday. It was presented at DEF CON last weekend. What is CPDLC? Controller Pilot Data Link Communications. And this is really important. It's akin to SMS. And the great advantage of using this system is instead of having to do radio, we can just send a message. Now, radio, as a pilot, I'm continually having to listen out for the controller saying something to me, instantly got to dial into it, got to hear it. If it's complex, I've got to write it down, and then I've got to repeat it back so they know that they heard me, which can be quite distracting when you're busy on a flight. So, what is CPDLC? So that is our Airbus A320 simulator. Come and fly it sometimes, quite good fun. And that little screen there, so when you get on your next 320, look left, and you'll see the CPDLC sign. What does it do? So it sends messages, and the good examples here. So this is a changed frequency message. So rather than jumping on the radio, and if I was in a British Airways plane, and I got this message, so for example, the controller would say, Speedbird 241, change frequency, Echo Delta Yankee Yankee, Maastricht Center, 123.085. Then I've got to repeat it back going, change frequency, Echo Delta Yankee Yankee, Maastricht Center, 123.085. All right, so it takes my time, it jams the airways, no one else can speak. So much better if you can just send it to me, and I hit Wilco, will comply, or I can't do that for some reason. Well, you can print it. I don't know why you want to print it. Anyway, it's another story. So that's an easy one. But next place it gets, so this is more complex. So this is actually very relevant. I'm sure some of you might have been this way. So let's decode this CPDLC message. So it's from Echo Golf Sierra Sierra, that's Stansted. This is your flight clearance on the ground, which would be done over radio, and I'd be having to write stuff down. I might get it wrong. I might listen to the wrong things. Good. So what have we got? You are cleared. This is your clearance to Echo Golf Papa Foxtrot, Glasgow. Handy. You're going to be using runway 22, and you're going to depart using Atava 1 right. What the hell is that? Come on that in a minute. Squawk 7701, that's my transponder code. ATIS, that's the weather. I need you to listen to the ATIS alpha, and that will tell you what the weather's doing at the airport in departing. When you're ready, call, that's the ground frequency to 121.725, and now I can go, Roger. Great. What the hell does that lot mean? What is UTVAR 1 right? That is it. So that is a standard instrument departure. And what this does is, in the case of 7 characters, I can communicate all of this to the pilot. So here is Stansted. What do I need to do on my UTVAR 1 right departure? So what it tells me as a pilot is I take off, and I can go to 3 nautical miles from once I'm airborne. I then turn to intercept the 170 radio from the Barkway VOR, which is a radio beacon, at 8 nautical miles. I can then climb to 3,000 feet at 5 miles and finally to 4,000 feet at 2 miles, at which point I start my left turn towards Otava, which is an instrument flight rules reporting point on the 263 radio. So 7 characters told me all of that. Now, these IFR reporting points have got really weird names. Some of them mean absolutely nothing, but some of them are actually quite funny. So if you try and do a departure from Portsmouth in New Hampshire, and you do a particular departure like this, the 4 IFR departure rules are, I taught, I tore, a putty, cat. And there's one coming out of Providence, Louisville in Kentucky, which is, the first one is Luke, second one is I am your, and the third one is Father. I thought, okay, that's quite random. Anyway, so that's what that CPDLC message is told. That's what the AI does when you put it together, and that is the talk that Martin Strohmeyer and a guy called Mehdi Ziazi did at DEF CON last week, and it's really, really interesting. I'll summarize it for you really quickly. So that messaging system, the plane has to log on to an air traffic service unit. They then do some messaging exchange. They authenticate each other, and the plane and the ground controller can now send messages to each other. What the team got to the point of doing is, in theory, it appears that you can cause a de-authentication, which causes the plane to be knocked off the ATSU, and they can now talk to a rogue ground station. I'll be honest, I'm still in some debate about whether you can actually de-auth a plane. I'm waiting to talk to Martin in more detail about it. If you do drop out of coverage, which you'll do, for example, Mid-Atlantic, Mid-Pacific, absolutely agree with this. There is one other slightly weird thing. I'm going to talk about GPS in a minute, is if you spoof GPS time, so the CPDLC clock is out of sync by more than a second with the ground station, it'll drop. And there's a great opportunity there as well. So this is a really interesting paper. I thoroughly recommend you read it. Other ways that you can do stuff. You can also do it with electronic flight bags. What is an electronic flight bag? Well, again, look left when you walk into the plane, and you'll probably see the pilots working on a couple of iPads or similar computer. And they are awesome, because when I used to fly, I used to have a massive bag of stuff which contained all my approach plates and charts. So it's telling me how to arrive at an airport, it's telling me how to navigate between, and they keep getting out of date. Every 30 days, I need to have updates to that, literally changes in airspace. So incredibly complicated, a lot of paper hanging around, or you can have an iPad. Brilliant. Fantastic. So what do these things do? They do loads. Most importantly, they do engine performance. We'll talk about that in a minute. They do weight and balance, so they make sure the plane's balanced, so we don't do the Airbus A380 thing I suggested. They've got the passenger information list, so they know where all the passengers are. And there's loads and loads of other stuff they do as well. Problem is, it's not always very locked down for all sorts of reasons. I know one airline that their PIN for their iPads, their EFBs, is the pilot's birthday, which of course is largely open source data. In smaller operators, we've seen pilots being told to go to Best Buy or wherever and source their own iPad, which is crazy. And even those operators who've got a really good proactive stance on those devices often do things that don't help, because we think about locking down those devices with our ground-based head. So when you do a mobile device that attaches to corporate systems, you get an MDM and it locks after 10 seconds, and you can, etc. Problem is with pilots is you might think, let's use biometric authentication, fingerprints, Face ID. Great, means I can unlock the device really quickly. And one of the problems that creates is if I've got a safety incident aboard the plane, one of the things I'll do immediately is look at my Electronic Quick Reference Handbook, EQRH. And that is to troubleshoot or deal with an incident. And a great example of an incident is a depressurization event. Maybe the door plug's popped out. So all of a sudden I've lost pressure in the cabin, the rubber jungle's dropped in the back, so everyone's on air masks, I need to get down quickly. And at that point, I'll probably be putting my own mask on, so I've got oxygen as a pilot. Also, because I'm cool, and I always fly in lovely blue sunshine above the shitty clouds and weather, I've always got sunglasses on as well, and they're always mirrored, which makes Face ID really difficult. And secondly, if I'm wearing a mask, how the hell am I going to unlock that iPad that needs biometric auth to unlock my quick reference handbook and diagnose the emergency? I'm screwed. I'm not going to take my mask off, jeopardize safety of the plane in order to unlock the iPad that tells me how to save the plane. Not a great idea. But even without that, some related things that have gone wrong, even without cybers. And a good example here, so American Airlines, a good few years ago now, they suffered an issue with their Jeppesen charts. So the charts, the maps, the approach plates, and there was a duplication in one of the electronic flight bag apps that served the pilots their charts. The approach plates for Reagan National Airport next to Washington, D.C., were duplicated, and that caused the entire iPad to lock up. So nothing worked. Thousands of flights didn't go that day. There was another one with Southwest. They lost their weather feed to their EFBs. Now, you might think, well, I'll look out the window. It's raining. It's not raining. No, we need to know about the weather up there and where we're going. So you need your weather feed. It's really, really important. And then another one. You can read this report, actually. It's Golf Uniform Zulu Mike India. You can read the report on the AAIB website, part of gov.uk. They had a very last-minute change of plane type between the A320 and the A321. But the load sheet wasn't changed. There was a sync issue, which meant that they didn't get the new load sheet. Now, as you probably know, the 320 is shorter. 320 is longer, but because the load sheet wasn't moved, the passengers were loaded as if it was a 320 towards the front of the plane. And that resulted in an out-of-balance condition. Now, this is the EFB application, and that is the weight and balance envelope for the airplane to where it successfully take off. And that is outside the envelope, and that was the weight and balance condition of the plane. What happened? Pilot puts the power on, trundles off down the runway, gathering speed, gets to his computed VR, rotation speed, pulls back. Nothing happens because there's too much weight at the front. Now, this is why we need pilots in planes, because that very well-trained pilot went, oh, okay, I'm going to add more power, continue to accelerate, and finally got to the point where there was enough elevator authority to lift off. The reason the plane actually staggered into the air is because the engines hang off the wings. That rotational moment forced the nose up. There was no safety incident. The flight continued, everyone landed, it's absolutely fine. But it's amazing what one simple issue with a flight bag application can cause to safety. I talked a moment ago about engine performance. Now, one of the things you might not appreciate is when we take off in a jet, we very, very rarely use full power. Almost unheard of. The reason we don't do that is because we don't need it. So if I don't use full power, if I've got a nice long runway, I can use less power. I can derate the engines. So if I'm fairly light on people and fuel, I can get down in a 737 as little as 50% power. The reason for that, we don't want to use as much fuel. We can save fuel. We save wear on the engines, great, so we save money. And we also stick less carbon dioxide out as well, keeping our environmental creds up. But that derate calculation, on a Boeing plane, it's called derate. On an Airbus, it's called a flex temp departure. We put in some information using our electronic flight bags and calculate that derate. Some things went wrong in Lisbon Airport a little while ago. Now, they would do some work on some of the taxiways here, and the taxiways had lots of temporary markings on. And as a result of that, it confused a bunch of pilots. So typically, a regular plane, so a 320, 737 short haul, would probably depart from around here, giving you about 1,800 meters of runway. The heavies, 380s, 747s, would go from about here, giving you about 3,000 meters of runway. But what was going wrong is because the pilots were putting the wrong runway intersections in, they confused the performance calculators into thinking they had 3,000 meters of runway when they were actually here. And as a result of that, they had too little power, only just took off, were about 50 feet in the air once they got to the end of the runway. And whilst they infringed what's called the screen safety height, there was actually no direct safety impact. But imagine if that had been just slightly wrong. That was very quickly addressed. It happened to 8 flights in very quick succession, and stuff went sideways. It's also happened with this incident, absolutely fantastic case of an airline being on the button. They had updated the software on their electronic flight bags. The performance calculator wasn't working properly and spat out the wrong information. And very quickly, one morning, they had 2 tail strikes, and they analyzed that data in near real time, warp speed, and realized there was a problem with the performance calculators in the software update and did a ground stop. They stopped everything moving that day. I mean, that is an incredible safety record. But they still had 2 tail strikes. We get about 2 tail strikes a day around the world just through poor pilotage. It happened again with their weight and balance application a little later, but it's a great example of how software can lead to safety consequences in aviation. It can get worse. This is a case of a really bad tail strike that happened where the crew inputted the wrong fuel weight on a plane. They got rotation speed wrong by about 30 knots, so instead of taking off, they just dragged the arse out of the plane. They only discovered they have a problem, missing half of the plane. They'd actually damaged the pressure bulkhead and only realized they had a problem when they got to about 10,000 feet and the plane wouldn't pressurize. So then came down and realized they'd lost most of the tail. Bad day. And this one on the right is really sad, actually. This was an incident where a very tired 747 freighter crew misentered their weight by 100,000 pounds, which spat out the wrong D-rate information for the engines, and they never actually made it into the air. I suppose, thank goodness, it was a freighter, but even so, 3 people still lost their lives. So that's what can go wrong just through mistakes. So what we wanted to know is whether we could actually inject similar mistakes through security vulnerabilities. And it's not just takeoff, it's also landing as well. This is an incident in Quito Airport in South America. It's notoriously difficult, lots of crosswinds, very challenging approach through mountains. And the pilots miscalculated their braking requirements. So believe it or not, you can actually choose between about 5 different braking settings. And the reason you don't go heavy all the time, it's painful, it heats up the brakes. If you go really crazy, you can set fire to the brakes. So we don't use Auto Land 5 very often. They chose Auto Brake 2, they should have used 3, and as a result, overran the runway and trashed the plane. Real shame. So can you make stuff go wrong? So here's a series of vulnerabilities we found in electronic flight bags. We saw stuff go wrong. This is Boeing. This is their onboard performance tool. This is their electronic flight bag performance calculator. We discovered through a lack of client-side validation, you could actually tamper with runway lengths, for example. So instead of the calculator thinking it had 3,000 meters of runway, we told it had 10,000 meters of runway. Hence, the plane thinks it's got miles to build up speed. We can save loads of fuel, and it derated too hard and got the V-speeds all wrong. So it would just run over the end of the runway. This is another one. This is in the 747. It's a quasi-retrofit. It was an electronic flight bag that was kind of bolted into the plane. And in wonderful Windows 7 kiosk breakout mode, control, shift, escape. OK, we're out. Then discovered that, oh, OK, password. Great. Security is great on planes. And yeah, whilst there are 2 of them for redundant purposes, you always have 2 of everything on a plane, sometimes 3. Actually, they're networked together, so you could attack one from the other. So the cross-checks that pilots do would have said the same bad data. We also see a lot of stickers over things in aeroplanes, inoperative or don't use this. So the USB port on the side had a sticker over it, which we promptly removed, and you could bash bunny the hell out of it, and yeah, great. Only needed a few seconds. But it's not just Boeing, it's also Airbus. I would say Boeing dealt with that really well. It took them 2 years to fix it, but they kept us updated every single week. They did a really good job of it. Airbus, this was their version. It's from one of the subsidiaries called NavBlue. It's a package called FlySmart, less paper cockpit, next generation. And it had exactly the same vulnerability as the Boeing product. They decided that fixing that would be a product improvement. So they declined to fix. So I called the EASA, the regulator, and they said, hold my beer. Now it's been fixed. There's another one as well. This one made me laugh because it's been a long time since you could successfully exploit Wi-Fi. Reason being is that most traffic is encrypted by default. Well, another one of their apps, this is the FlySmart Updater Suite, so updated all the software packages on the EFB. We were looking at it and realized they'd intentionally updated application transport security. They'd intentionally disabled it, so it wasn't validating that the packages were signed. It was allowing any traffic, so you could man the middle. Now, chasing planes around is hard, but actually, pilots always lay over in the same hotels. So as long as you know which hotel, every single night there'll be a crew there. So now you know where to go and find crews to do this attack. In fairness, Airbus have fixed that very quickly. It's not the only type of issue. We also found some problems in a Lufthansa product. Lufthansa have a subsidiary called Lufthansa Systems that do software packages. Really cool bit of charting pack. This is eRoute manual, which contains the maps, if you like, the charts, the approach plates, departure plates. They had basically the same vulnerability as the Boeing and Airbus products, but they did actually validate that integrity. They did it using an AES key. Unfortunately, the AES key was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 3. But anyway, that didn't take very long. What that meant was you could tamper with the approach plate data. Now, this is an approach plate for a non-precision approach. And by that, I mean there's no instrument landing system. So I haven't got the crosshairs to follow. I've got to use a radio letdown procedure. So to explain what this means, so I arrive at 5,000 feet, and I'm safely above terrain. I get to my initial fix, which is at distance 14 from the BRA VOR, which is over here. I can then descend to 4,600 feet to 12.4 miles, like my top of descent. I then approach an angle of 170 degrees magnetic down to DME 9. Final fix, 3,900 feet. I'm now safe to go to my minimum descent altitude until I hit the middle marker at 4 miles. And I can either now look at the runway, or I can go around and try again. Unfortunately, because we could tamper with the data, we could change all of these, and therefore the plane would descend, the captain would be very happy, thinking he's safely above terrain, and then flies into it. Controlled flight into terrain, otherwise known as a crash. Bad day. And then we see other really mad things. This is part of a talk I gave at DEF CON about some of the consequences of GPS that we haven't really thought of, and blew my mind that you could potentially ground a fleet of airplanes with a software-defined radio. Let me explain. So, GPS, there's loads of content out there. I strongly recommend you follow the Ops group, which is a group of aviation operators. I've contributed to some of their data. Now, we all know about GPS jamming and spoofing, and the consequence being you lose GPS or you think you're somewhere else, which is kind of bad if you're operating close to a hostile territory like Russia, for example. We've seen it in the past around Black Sea. As a result of various of the conflicts we've seen around Ukraine, for example, we're seeing a huge spike in use of consumer drones as weapons, which use consumer GPS rather than military GPS, which is protected. So we've seen a huge spike in jamming. Now, one of the initial challenges we might see is when we're doing an approach using an instrument landing system, we've got radio fix, we're flying safely down the approach. At some points, we've seen, for example, on approaches into Tel Aviv, for example, the GPS is being spoofed, thinks it's somewhere else, and all of a sudden the ground proximity warning system goes, whoop, whoop, pull up terrain, because it thinks you're about to fly into a mountain, because it thinks it's there, even though the instrument landing system is correctly sending you down the correct approach. What do? You go around, you try again, you disable GPWS, and then you land safely. But it's caused all sorts of problems. We've seen some really interesting consequences. It's one thing having a GPS spoof. What we've started to see is poisoning of other systems, because GPS is more accurate. It's more accurate than radio navigation. It's the best, right? We love GPS, so we use GPS. Problem being is, because we trust GPS so much, many of the systems on the plane will update themselves from GPS to be more accurate, which means you get nutty scenarios where our backup system, our inertial reference system, so that's laser gyros, which can do about a nautical mile of precision over 3,000 miles, but not as accurate as GPS. They're updated from GPS, so now we see poisoning of other systems in the plane. It's not the only one either. We've also seen some consequences around the receivers that you use. Now, in order to acquire GPS quickly when I'm stationary, we use a GPS almanac. So that's why your watch can pick up GPS quickly, because it knows roughly where the satellites are supposed to be. If you've been through a period of jamming for, say, 20, 30, 40 miles, by the time you emerge from that area of jamming, the position of the satellites in the sky will have changed. So when you try to reacquire, nothing's in the right place. And we've seen numerous flights no longer able to use GPS for the remainder of the flight after going through a relatively small area of jamming. The only way to reset that is get back on the ground, power off reset, it reacquires the almanac, and now you can fly with GPS again. Why is that a problem? Well, if I don't know where I am, I've got to speak to air traffic control, and they've got to give me an upgraded radar control service and really look after me. But there's lots of planes going through that area of jamming at the same time. So now all of a sudden the controller gets overwhelmed, and that's when we start to make mistakes. The good news is the later receivers, so much more recent receivers, are much better at doing this. Yeah. Some crazy stuff going on as well. There was actually a flight in Tartu, Estonia. They actually had to retire. They'd actually retired their original radio-based expensive ground navigate. So the instrument landing system is expensive to maintain. So we've got GPS approaches now, so they retired it. And now they're being jammed to hell. And Finnair couldn't go there for a while because they didn't have a reliable source of landing information. So we're rushing to retire our ground-based radio navigats in favor of GPS, and now we can't trust GPS. So we could be in trouble. But the one that really freaks me out is not about position. Actually, GPS is time. Right? We're using time and time differentials in order to calculate our position. Time is quite scary. We've seen some issues around time moving a little bit, a few seconds, and the instruction to pilots is if they experienced any sort of spoofing or jamming, change from the GPS clock to the plane's local clock, which requires manual intervention. So that's the instruction. I'm not going to tell you who, but there was an incident a little while ago where a plane entered an area of jamming and spoofing, and then time jumped into the future by a significant period of time. And the pilots weren't able to intercept and go to manual time before a bunch of other things had happened. This caused lots of mad things to happen. So the first thing that happened is the passenger Wi-Fi went offline because GPS is the trusted source of time, and all of a sudden the digital certificates were no longer valid. They hadn't expired, which is what we usually experience. They were just no longer, they weren't valid yet. So we had no trusted source of time in order to validate our encryption. So the passenger Wi-Fi went offline. The next thing that happened, back to CPDLC, because the time was wrong, the controller pilot data link went down. So that didn't work either, which meant the only thing they had was VHF, radio, in order to navigate their airplane. So that massively increased their workload. Really scary time, actually. Now, other crazy things happened. Because you can't roll GPS time back. You can roll it forward, for example, leap seconds, which happens every few years. You can't roll it backwards again. So that caused chaos because it couldn't reset the time. So they had to reflash pretty much every single LRU on the airplane. And that took the plane out of service for nearly 2 weeks. So one SDR doing a bit of GPS spoofing knocked a plane out of service. That's crazy, right? Now, the good news is the engineers are learning very quickly how to reflash and reset these systems. And there's a lot of work going on to make the systems recover better. But even so, one SDR, one spoofing incident, one time jump, and all the systems are knocking offline. Not a good day, is it? Anyway, the good news is increasingly there's been a lot of work done on hybrid GPS. And that is using ground-based systems, so for example, our radio navigation layers like a VOR, an NDB, etc., to check for course position moves. So if there's a 20 nautical mile jump, check the ground still where the ground should be. If it's not, something's up. So there's a lot of work going on there. But in the meantime, the bit that makes me nervous is we're rushing to disable our expensive ground-based radio navigats before we can really trust GPS. I want to move on and have a bit more fun, go back into the cabin now and talk about some fun stuff we did on some old 747s. Now, one of the problems with these, this is the cabin management terminal on the 747. It's in the cupboard underneath the stairs. It does all the passenger IFE. It can do some ground-to-air communication. It can even take a credit card charge as well. Now, we wanted to play with this, and the first thing we had to do is pick all the fluff out of the Ethernet port. That was fun, but we successfully interfaced with it. And this is a plane that last flew in 2020, and there is Windows NT Service Pack 4 with the build date of 1995. Wow. I don't know about you. I've forgotten how to interface with Windows NT. That's a very, very old day, but it's lovely to see DOS in there as well. You couldn't even net send, which was madness. But look, that's a plane that was flying until a few weeks before it was laid up for COVID. That's madness. Another crazy one. Do you remember I talked about compromising IFE earlier in the talk? Well, this was another cabin management terminal, a different brand, and we discovered if we could access it locally, we could recover its AWS S3 bucket credentials. We could get them compromised. That gave us full read-write access to an AWS environment, which was being used to update the media on all of the in-flight entertainment systems for that particular fleet. Imagine how much fun we could have had by putting donkey porn on that. Now, We didn't, obviously. What we did is we ethically disclosed to the vendor. They were like, shit, thank you very much. They got it fixed within about 2 weeks, and now that vulnerability is not there. But we did have to have physical access to the plane. So the chances of us, I think, doing it for real were pretty limited. Other crazy stuff, so the in-flight Wi-Fi, sometimes you see really good rugged installations. Sometimes you see a quasi-consumer router in a cupboard somewhere with the password written on the back of the door. I'm like, wow, this is war games all over again. Yeah, anyway. This one, we've actually done a bit more on that one since. It had onboard media servers as well, so we pulled one of the SSDs out, forensically imaged it, and madly in Slack space found some photographs of, we think, the IFE engineer had used one of the SD cards on there to use in his camera before he loaded it into this IFE server. So we've got some photographs. I think it's Detroit Pistons of their ground with him in front of it. It's like, wow, that's not what you expect to find. And the other bit that I think is really important is it's key to understand that when we update planes, you can't just go and dick around with new software on the airplane. Yes, you will still find floppy disks on some older airplanes. There are still 747s flying with their nav databases updated on floppy. That's a 737-200 series data loader still on floppy. It's really irritating for the engineers because they have to go onto that plane every 30 days to put disks in to update the navigational databases. What a pain. More recently, things are getting much, much better. So we've got the concept of signed air parts. So you'll find any later plane has cryptographically robust updating processes which are done from something like a maintenance laptop that looks a little bit like that. You need a special interface, a special laptop that will connect to certain controllers. When there's weight on wheels, so you're not in the air, you can update the software. But it's done really well, and I'm actually really impressed. It's just older planes where there's a bit more complexity involved. So given we've got a couple of minutes left, I thought I might have a bit of fun. Now, why am I talking about airplane hacking in the movies? Well, again, I told you I'm not a shouty person, but I get shouty when I see misleading tropes be repeated in TV shows and in the movies. So I thought it's really important to actually talk about some of these and talk about why some of the things we see in movies don't actually work. Because I don't think it makes the traveling public feel any safer when they're thinking about flying. There are a lot of nervous passengers out there already. My wife isn't a great flyer, for example, doesn't like the turbulence very much. But even worse, if we spook the traveling public from what is fundamentally the safest way of traveling. So, in terms of one movie that we think represents plane hacking, anyone got any out there? Who's going to shout it out? Die Hard 2, yippee-ki-yay, motherfucker! The best plane hacking movie out there. So how does it work? For that, I want to show hands now. Has anybody not seen Die Hard 2? Good, I'm going to spoil it for you. Anyway, it's been around a while. So what's the plot? Well, the idea is some terrorists are trying to rescue their leader who's been arrested, stuff goes on, and the idea is there's a plane that is coming into Washington Dulles on the ILS. They've compromised the instrument approach system. There's a snowstorm, and resulting in Cat 3 autoland. So that's zero visibility. Cat 3C means I can't see shit. I can't even taxi to the terminal. There's a bit of a problem, though, is that the first plot hole is that you can't make a movie in Cat 3. That's fog. I can't see anything. So that's what Cat 3 really looks like. And the plot is that the instrument landing system intersection with the runway has been dropped by 200 feet. So plane lands, crashes, bang. Okay, all right, that sounds a bit plausible. So first problem here is, if that was the case, if there was genuinely, Dulles was socked in with fog or whatever, then I'd go somewhere else. And my instrument flight rules flight plan, that is it over there, will always specify my alternate airport. So you see I've got an alternate there and a second alternate. I cannot take off and go there if I haven't got somewhere that I've got an alternate which I know the weather's going to be good at. And the great bit about it is there's lots and lots of airports on the east coast of the USA. So where is Dulles gone? That's Dulles over here where it's all done. I can go to Reagan National, I can go to Edwards Air Force Base, I can go to Baltimore. There's loads of options for me on the way. So you just wouldn't get into this scenario in the first place. And then what happens is one of the terrorists turns the altitude wheel in air traffic control. So now, I've been into a lot of air traffic controls, and I've never seen the altitude wheel. Anyway, they spent a bit of time actually here. This is nice. They actually got a nice digital interface and used a light pen, oh cool, how old, and dragged the instrument landing system down. They even spent a bit of time getting things like the middle marker there, and they got some of the glide slope correct. But you can't do that. It doesn't work, despite it being quite well made. So what's the problem? Well, what they suggest is that they've dropped the intersection down by 200 feet. And this is where it all goes wrong, is because when we're descending on the instrument landing system, we're actually descending at about 700 to 800 feet per minute, depending on our weight, depending on headwinds, tailwinds, all these sort of things. So 700 feet per minute is not a crash. It's a heavy landing. So there are planes out there, that the BA-146, its undercarriage can withstand 1,500 feet per minute of down. So the 747, yeah, it'd be a heavy landing. There might be a bit of damage. You probably want a maintenance inspection. But the first problem is the attack doesn't work, right? So you just hit hard and spill your drinks. Anyway, so the ILS, as I explained earlier, all you have to do is fly down the glide slope, and the localizer keeps you aligned. So it just doesn't work. That's what it looks like. Can you screw with it? Could you mess around? So that's the localizer antenna. What can you do? Well, you can change the glide slopes. That's the angle you descend at. So in this case, that's London City. London City is unusual. It's actually got a 5.5 degree approach, so you don't fly into HSBC on the way in. Paris Charles de Gaulle is at 4 degrees, but Heathrow and most airports are at 3 degrees. So you can change the glide slope. But the thing you can't do is you can't change the intersection because there's a physical beacon there. The only way to do it is you can actually, in theory, dig a 200-foot deep hole and put the entire ILS array in it. But I don't think that would work. So this was Lelystad, and what you'd have to do is basically that. So quite an involved attack. Anyway, there's other plot holes as well, so it's not the only way we monitor our approach. So in Cat 3, we use our radio altimeter, which will give us a very precise, effectively a sonar ping like a submarine. It gives us a very, very precise altitude. And in Cat 3C, where the flare is commanded by the autopilot, that's great. Now, there was some good research around this. It wasn't just about 5G interference. There was some great research around, hey, actually, could I cause the plane to flare too high and land hard, or not flare and land hard? Yes, but it's still very technically complicated. There's other ways, so we monitor, even today with GPS, we still monitor our distance measuring equipment, so the DME is just there. We check it once on the approach, so we see that was wrong. The integrity of the instrument landing system is monitored by ATC as well, so none of this really works. So how would I have done it? So what you could have done is take it offline, which involves chopping some power, so Heathrow lost bits, as you remember, or take it offline in dodgy conditions and force the planes to use that non-precision approach I talked about. And it happened. This is an incident report from an approach into Paris Charles de Gaulle. It was a couple of years ago, and it was a non-precision approach because they were doing maintenance work on the instrument landing system. They were calibrating it, so it was offline for a period of time. And there was a miscommunication between the controller and the crew, and they got the air pressure setting for their altimeters out by 10. Now, 1 millibar is 30 feet, so 10 millibar is 300 feet. And as a result, the crew descended below their minimum decision altitude, which is where you look out the window and go, no runway, go and try again. They came within 6 feet of hitting the ground a mile from the runway threshold. There's a better illustration there. You can see they very, very nearly crashed into the ground through a miscommunication. Crazy, right? So that's how I'd have done it. If you wanted to die hard too, it'd be really cool. But anyway, I'm going to finish now. I just want to leave you with a little bit of advice that flying is very, 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 very safe. The industry has thought about security in the same way it thinks about safety. It's baked into the network architectures, it's baked into their protocols. They've really thought about it. Next thing is, do not go hacking planes unlike the dickheads on Delta Flight 591, right? You're going to get arrested. They know you're on board. They can just wait at the gate and arrest you. Really bad idea. There are, if you want, there are some retired planes around you can play with. You can go and get some components. I'm hoping to host an event on a retired 747 next year. I'll let you know how that goes. There's technical debt, though. Don't get me wrong. You do still find really old systems out there. Last couple of things, if you do find something, disclosure is different. Because of the certified nature of software, you cannot do Google Project Zero and expect remediation in 90 days. It's going to take a year to 2 to get the fix done properly. Take your time. If something's not going right, let me know. I'll gladly help you, or we can put you in touch with the regulators, and they will help you as well. There is research going on, not very much, because the community is really small, mostly because the barrier to entry is huge, because you have to go and buy a plane, and they get expensive. But there are groups around, so we helped get the DEFCON Aerospace Village off the ground. We've just come back from there. It's brilliant. We had 12,000 feet of amazing stuff going on. And also the Aviation ISAC, which I'm sure Sean will give a plug for a bit later, is a really good community for the industry to get researchers, communities, and operators and manufacturers talking and communicating. It's really, really important. We do cool stuff, but do it in a careful way that improves safety, improves the confidence of the traveling public, and makes aviation safer for everybody. That is me. There's a few talks online you can see. They'll be on the DEFCON media server. So as a primer for testing AFDX, I'm talking about light aircraft TCAS as well, and how the cyber pilot has started to evolve as a role within certain airline operators. Thank you very much for listening.